Welcome back to Honors Calculus. In this video, we will continue our discussion of differentials with the idea of related rates. This is really a side track on our quest towards differentials. In the last video, we were talking about implicit differentiation, and the related rate is the classic application of implicit differentiation. As you can see, I already have a problem written out here, so let's dive in. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. And our question is, what is the rate at which the diameter of the balloon is increasing at the point when the diameter crosses 5 feet? So visualizing this problem, I am quite certain that each of you has at some point in your life seen a balloon being inflated. As you blow air into the balloon gets larger and larger. The larger the balloon is, the less the size of the balloon seems to increase every time you pump more air into it, because there's a lot more space for the air to fill in. There's a lot more surface area to be pushed against, and so on. So, in our quest to solve this problem, we need to think about how to represent the change in volume, how fast the volume is increasing. That's exactly the job of the derivative. So the known information is that v prime, the derivative of v, is 4.5 cubic feet per minute. And of course, we know that the volume of a sphere is given by v equals 4/3 pi r cubed. Now, a little bit tricky here, because our problem is not asking us about the radius of the sphere, it's asking us about the diameter. So we know that the radius is 1/2 of the diameter. So let's go ahead and plug that into the equation. So we have v is 4/3 pi times 1/2 d cubed, and we can cube those things separately. 1/2 cubed is 1/8, d cubed is d cubed. And we have our our 4/3 and our 1/8. There's some stuff that will cancel out, reducing that. And we have in total, the volume here is pi over 6 times the diameter cubed. If you happen to know that formula offhand, then you can jump right into it. More people are familiar with the formula of volume given in terms of radius. And if that's what you know, it's a pretty easy derivation. Now, the trick here is to realize we have a variable v, we have a variable d. We're not interested in the derivative of v with respect to d. We're interested in the derivative of v with respect to time, t. So the derivative with respect to time of v should be equal to the derivative with respect to time of pi over 6 times d cubed. And the derivative of v is v prime. The derivative of pi over 6 d cubed becomes 3d squared. So we've got 3 pi over 6 times d squared, but then we have to multiply by the derivative of d, which is d prime. And we can reduce that fraction a little bit and get that v prime is pi over 2 d squared d prime. Now we get to use our knowns. Now we have derived a formula that relates the thing we care about, d prime, to some stuff that we know how to figure out. We're given v prime, we're given d. Right, scrolling back up in the problem, I wrote down that v prime was 4.5. I didn't write it down before, but we do also have that d is 5 feet, which is important. First of all, that we're going to need in this formula, but more importantly, I didn't plug in that value of d just yet. The rate of change is looking at how d is changing. So we can't have a particular value in d when we derive the formula. But our end goal is to have a formula for that involves d, so we have to have a particular value we can plug in at the end. So we plug in that v prime is 4.5. We plug in that d is 5. Since we're already given the decimal value 4.5, I'll go ahead and grab my calculator and calculate pi divided by 2 times 5 squared, which is about 39.3. And then divide by that thing to get d prime by itself. At the point when the diameter passes 5 feet, pumping 4.5 cubic feet per minute into the balloon. We have units of feet and minutes going on, so we know that this result, 0.115, is in feet per minute. 0.115 is about 1/9 of 12 is about 1 1/3. So about 1 1/3 inches per minute is the rate at which the diameter of the balloon is increasing at this point. If we look at a place where the diameter is smaller, right, we've already done all of the hard work, so we can very simply look at a related problem . What about when the diameter is 2 feet? Well, in that case, we still have v prime is pi over 2 d squared d prime. I'm assuming that we're still pumping air in at the same rate, 4.5 cubic feet per minute. Right, now we punch in pi over 2 times 2 squared, which is about 6.28. And if we divide both sides of the equation by 6.28, we get 0.72. Something in the ballpark of 9 inches per minute, quite a bit faster than the first calculation. Let's look at one other situation. In an engine, a 7-inch connecting rod is fastened to a crank of radius 3 inches. The crankshaft rotates counterclockwise at a constant rate of 200 revolutions per minute. And we want to find the velocity of the piston as theta passes pi over 3. So the idea here is that this crankshaft is rotating fairly rapid rate, 200 revolutions per minute. And as that crank rotates, it's going to cause this piston to move in and out of the cylinder. Or in fact, if you know anything about internal combustion engines, you know it's actually the opposite. An internal combustion engine works by creating a very small fire right here, and the expanding gas pushes this crankshaft or pushes the piston out, which causes the crankshaft to turn. Momentum, or a piston that's off cycle, causes the crank to continue to turn, pushing the piston back in, creating the ideal circumstance for another controlled explosion, which will push the piston back out again, causing the crank to continue to rotate. So our setup is very different from how you might approach this as an engineer trying to design the engine in the first place, but it gets the job done and it's still something we can do. So we know that we are looking at a particular time when that angle is pi over 3. And we can use the rate at which this is rotating to figure out how fast this little piece is moving. To solve this problem, we're going to have to think a little bit outside the box. The first thing I'm going to do is redraw the picture with as much detail removed as possible. Because what really matters is that we have a radius of the crankshaft between the center point where we're measuring the angle and the point where we are connected. We have an angle there we'll call theta, and a constant fixed length here of 3 inches. Then the crankshaft is attached to the piston with another rod of fixed length 7 inches, and it's set up in such a way that the piston is along the same axis where we are measuring the angle, right? That's kind of how we determined what that angle meant. And so what this problem is really asking is, if I look at the third side of this triangle, let's call it length L. What we need to know is, how fast is this length L changing? We've got a triangle. We know 2 sides of the triangle and 1 angle of the triangle. Whenever you are looking at an oblique triangle, a triangle that doesn't have a right angle or doesn't necessarily have a right angle, relating 2 sides and 1 angle, you can set up something using the law of cosines. Which tells us that little c squared is little a squared plus little b squared minus 2 times little a times little b times the cosine of capital C, where capital C is the measure of the angle opposite side little c. So the place where we have an angle and an opposite side has to be the thing we call C. The other 2 sides, we have a choice. I'm going to go ahead and set A to be the constant of 3, and B will be the L that is changing. So using our particular values, we now have that 7 squared is 3 squared plus L squared, that's not a squared, that's a squared, minus 2 times 3 times L times the cosine of theta. Cleaning that up a little bit. We get that 40 is L squared minus 6L cosine theta. Unpleasant as it's going to be, we can differentiate implicitly both sides of this equation. So we'll take the derivative with respect to time of 40, and we'll take the derivative with respect to time of L squared minus 6L cosine theta. Right. Derivative of 40, derivative of any constant is 0. Derivative of L squared will be 2 times L times the derivative of L, which is L prime. And then we have 6L cosine theta. Right, that's a product of two things, so we're going to have to use the product rule here. The derivative of 6L is 6L prime, and then the derivative of cosine theta is minus sine theta multiplied by the derivative of theta, which is theta prime. Again, using the chain rule. Right. Rearranging this mess, right. L prime is the change in the separation between the crankshaft and the piston. That's the thing we're looking for. So let's solve for L prime. And we can find a common factor of 2 to reduce, I guess. L prime is 3L sine of theta over 3 cosine of theta minus L. All right, now we've got a bit of a problem. We know what theta is. We sort of mostly know what theta prime is. And I lost a theta prime somewhere in this derivation. Let's see, it should have been here and there and there and there. Right. We know what theta is in our particular use case. We can figure out what theta prime is. Right. The crankshaft is turning at 200 revolutions per minute. So in terms of radians, 1 revolution is 2 pi radians. So theta is pi over 3. Theta prime is 200 revolutions per minute times 2 pi radians per revolution, or 400 pi. We could get a decimal value, but it's not going to be all that useful. L is a little bit trickier. To figure out L, I'm going to have to go back to the equation I got using the law of cosines. I know that I'm looking at the particular case where theta is pi over 3. So I can plug that in here. Right? Cosine of pi over 3 is 1/2. And this is a quadratic equation. If we can find a couple of numbers that multiply to -40 and add to -3, we're golden. Otherwise, we can use the quadratic formula. And in this case, this thing does factor. In fact, it factors to L minus 8 times L plus 5. Right. L equals -5 is complete nonsense. You can't have a negative length. That's telling you that the piston shot through the crankshaft and out the other side, which is not going to be good for the engine. So let's assume that that didn't happen and go ahead and let L be 8. And then we can plug everything into our equation. We get that L prime is 3 times 8 times the sine of pi over 3 times 400 pi all over 3 times the cosine of pi over 3 minus 8. See, sine of pi over 3 is the square root of 3 over 2. So 3 times 8 is 24 divided by 2 is 12 times 400 pi is 4,800 pi square root of 3. Cosine of pi over 3 is 1/2. 3 times 1/2 is 3/2. 3/2 minus 8 is -13 over 2. And I mean, I guess we can figure all of this stuff out. Pi is about 3. Root 3 is about 2. Or you can just grab a calculator and let it do the work for you. And if you plug that into the calculator, you get something in the ballpark of -4,000. Let's call it -4,020. And let's see, my units were given as lengths in inches. My time was revolutions per minute. So -4,020 inches per minute. Really awful units of speed. If you're familiar with inches per minute, then you're in great shape. If not, you might want to convert it into something that's more to your style. Turns out that this is just shy of 4 miles per hour. All right, here's one for you to try. A tank forms the shape of a right circular cone, as I have depicted on the left. The radius at the top is 5 feet, and the height is 25 feet. The tank is currently being filled by a garden hose, which has a flow rate of 0.75 cubic feet per minute. The water level is currently 15 feet deep. At this point in time, how fast is the water level of the tank rising? I'd like you to take a couple of minutes, see what you can do with this problem, and I'll see you in the next video.